So today we're going to do a little bit more of the same thing. That is, we're going to actually, I hope, finish up the shell. And we're going to talk a little bit more about scripting with another language, right? Less scripting, right? So shell scripting. And in between, maybe simultaneously, we're also going to be talking about files and file names. All these are, to some extent, fairly basic topics in doing software construction, but, we're starting with the basics. So when we last finished, we were talking about how a shell command is expanded. Before it's executed. And to some extent, what you can think of this as being a process by which what you type into the shell, right? Here's your shell script. Gets transformed into another script that is written in a simpler language. It's an easier to understand language, but it's going to be longer to write the same code, right? So you can think of this as being sort of the expansion or expanded script. In a simpler language. And what the shell interpreter essentially does is it runs off of this expanded script. Okay. Now, the way I've said it here, I've made it sound like the shell takes your script and then mentally expands it into another file somewhere and then executes that file. But that's not really what's going on here, right? I should do a little bit of hand waving here, put quotes around this, because the expansion is occurring all the time. After one shell command gets expanded, it executes that command, and then it goes and expands the other script. So this expansion is going over and over again, right? This, in effect, is for each command. So it's not like you could write a shell preprocessor that would take a simple script and turn it into a big long script in a simpler language and execute that. Instead, the shell is preprocessing each command as you type it or as it's being executed from a script. And to some extent, what you have to do is see how that expansion works. Right? So let's look at sort of the stages of expansion in a shell command. And to some extent, stage 0 is going to be figure out where the command is before you start expanding it, right? So you can think of this as being delimit the command. Find out where it starts and where it ends, because if you don't know that, then you won't know what to expand in the first place. Now, what are some of the delimiters here, right? If you're seeing this long shell script with a bunch of text in it, how do you know where the next command starts? Well, first off, you look at the low-level tokens of the script. So, for example, if you see a semicolon sitting here at the top level, and it's not quoted or anything like that, then you know the command is going to stop there, right? Here's command 1, right? Here's command 2. So first, we're going to execute this command, and we're going to run it through all of these transformations, figure out what it does, go execute it. Once we're done, we'll then start worrying about this guy and expanding this guy. So there's going to be tokens that end the command, and The most common one, of course, is a new line. You type the command, you type enter, that's a new line character, that ends the command. But there are other things like, for example, semicolon or vertical bar. Vertical bar says we're going to take the output of this command and ship it into the input of the next command. So that's going to be another separate. All right. Second phase here is now we know sort of what's in the command. And we can think of the command now as being a sequence of words. Typically, a word is a bunch of, alphabetic characters, and words are separated by spaces. You can throw digits into that as long as it's not special. It could be quoted words, right? You can put whatever you want in quote marks, but your command is a series of words, and you start expanding them. And there's several phases of expansion. The first one is tilde expansion. Tilde expansion occurs when a word starts with a tilde, right? Okay, and the simplest one is this word here. Here's the word tilde. And that expands into your home directory, right? So for example, here, I can say echo tilde. What the shell is going to do is it's going to expand that tilde into the name of my home directory, which on CSNET is UCS-FAC Eggert, right? And in effect, the tilde gets expanded that way. Tilde expansion also will occur with a word that starts with this, right? Here's your word start. So if your word starts tilde slash, well, that'll be your home directory, followed by a slash, followed by whatever you want. Furthermore, if the tilde begins with a username, right? So the username might be Eggert. This is going to be Eggert's home directory, and tilde Eggert slash is going to be, your home directory followed by a slash. But tilde expansion is a little unusual compared to the other sorts of expansions we're going to see, in the sense that it doesn't work in the middle of a word, right? If I were to say something like this, echo E tilde, that tilde didn't get expanded, right? So it's only at the start of the word. All right, any questions about this one? This one's the simplest one, so we might as well get expansion done. All right, next one is going to be command substitution. I've briefly talked about that before, but I'll mention it again because here I'm going through all the expansions in order, and I'm figuring I might as well do them one at a time. This is the one where you can say $ open paren, put any command in here you like. This gets expanded into the output of that command, right? So we can do something like this, right? We can say echo tilde and get Eggert. We can say ls echo tilde, right? And this is equivalent to saying ls ucs-fac Eggert. Since I happen to be in that directory now, it's the same as just typing ls. Right? So you just take the command and you take its output and treat it as a shell command. Since this occurs after this, right? That means that if this thing outputs something that starts with a tilde, it's just a tilde, right? Because we've already done this expansion. The expansions are done in sequence. Oh, I've been telling you sort of what works. Now, I'm going to ask you, what's not going to work here? What sort of problems do you see with this approach? How can we get into trouble with tilde expansion or command expansion. Yes. So it would be invalid output. It's sort of a screw up, right? So we can say sort of like this, you know, echo, this is a bad, right? This is terrible command, right? Right? And then we can do an expansion of that, right? And then we can do a cat of that, right? So this is kind of a simple example, right? Here, what we're going to do is we're going to cat 3 files, the file this, the file is, and the file terrible. There are no such files here. The output of the command expansion could be something that you didn't really want to do. All right, suppose we do something like this. We'll echo exit, right? And then we're going to do something like that. What happens here? Right? We just logged out. Right? The output of command expansion caused our parent shell to crash. I'm going to have to go and reconnect to it now. So you have to be careful about this. In particular, you know, if this command is going to generate anything at all suspicious, you probably don't want to just go be executed right away. I mean, this is not so bad, right? Because here, no matter what it outputs, you're just going to basically output the same thing again. But if it's going to do something trickier, you might have trouble. Suppose we do something like this. Echo, I don't know, cat, etc. password. And then vertical bar grep Eggert. Right? Now, if I just execute that command, of course, it just outputs it as is. But if I do command expansion, right, notice that this might not have done what you expected. Right? Let's see what that command was again. So here, there's a $ open paren. Oh, I see. We need to raise the screen a bit here. There's a $ open paren. So we're doing this $ open paren here, right? We're taking all of that and we're treating the result as a command. But notice that since we're doing it in phase 2, phase 0 is already done. And so it is going to take that vertical bar as a file name, not as the end of a command, because we've already delimited the command. So you're seeing some of the consequences here of the phases that we're doing here. We're in phase 2. It's not going to go back and redo phase 0 again. All right. Next one. Oh, well, here's another thing you can do with this command. Suppose this command outputs binary data. What's going to happen? Just total gibberish. Well, the shell's going to take that binary data and try to interpret it as a command. You could get into trouble doing that. Third phase is going to be arithmetic expansion. And so nobody ever really confused the shell for a high performance sort of arithmetic system, but you can do very simple arithmetic in the shell with something that looks like this. Where this x here is interpreted to be the value of the shell variable x, right? So if we set x equal to, I don't know, 7, and then this will expand to the string 12. So you can add 2 and 2 to your heart's content with arithmetic expression. Now, there's a little bit of a conflict here, in the sense that I've already said this stands for run that command and take its output. And in a previous lecture, I said you can take some commands like this, echo x ERXY. And you can put them in parentheses, right? This means run this stuff in parentheses and, send the output somewhere or whatever. If you combine this notion with this notion, then you should be able to say $ open paren and whatever command you like. Here it is. That's a command. And this should mean, run this stuff. This out, it turns the X into a Y, and then run the, the command. But that's not what happens. In effect, this syntax takes priority over this syntax if you have the two open parens right next to each other. If you really want to do something like this, you're going to have to put a space here. The space is required to avoid what would otherwise be an ambiguity. To some extent, what's happened here is the shell has tried to have a very compact notation for lots of different ideas. And in this particular case, the ideas clash. And so we have a little bit of a glitch. You got to put a space here if you really want this mean. All right. Phase 4 is going to be field splitting. I think I left off a phase here. I have my notes here, and they don't at all agree with what I wanted. We're going to put another phase. We'll make it 1.5 here. Variable expansion. And this is just the normal stuff where if you have $X, you get the value of the variable X and that sort of thing. All right. So where were we? Oh, field splitting occurs now. Here, the idea is you've got a bunch of words. And you will want to sort of be able to split them apart into more words than you started off with, right? So maybe this one is going to expand into word, this is word 1, word 1A, and word 1B. Whereas these words just, this is word 2, word 3, these stay alone, but some of the words are going to split into multiple words. Classic example of field splitting will occur if you do something like this. Let's let X be the variable A space B, and then if we say cat $X, what happens in the field splitting phase is the shell looks at the value of X. This started off as one word. That's just a word. It's still a word till we get to phase 4. But it looks inside this word and it says, oh, well, it's got spaces in it. You really meant for that to be multiple words, which means you can now do something like this. Files equals A.C, B.C, right? And then you can say GCC $files. And this will compile both of these files together, right? It won't tell GCC, try to compile a file name A.C space B.C. Spaces are rare in file names. So the interpretation here is let's compile the two files. Let's run this command with 2 arguments rather than just a single argument. Now, when you do field splitting, there's an issue, sort of what constitutes fields. Right? And what that boils down to is what are the separator characters? And there's a standard shell variable that will let you specify the separator characters. And that variable is IFS, interfield separator. By default, this has kind of a strange value. It's a tab and a space and a new line. You don't actually write it this way. You write it as a 3-character string. I'm sort of trying to space it out, but you can put anything you like between apostrophes. So by default, IFS is these 3 characters. That means if you see any of those 3 characters in a word, well, then treat that as a field separator and break things apart. You can change this if you like. I don't recommend it normally. But for example, if I do something like this, I'll see $path expands to all of the sort of names in your path. Suppose you would like to iterate through those directories. Do something with it. Maybe list them all out, for example. You can't say this, because if you do, the colon is not treated as a field separator. So $path just expands into a single long string, and ls says, I don't know any directory with that name. Instead, what you can do is something like this. I'm going to save the old IFS into a variable, OIFS, right? We can look at it if you like. OIFS. So there's a space and a tab and a new line. It kind of looks like a bunch of nothing, but that's kind of what it is. But now I can say something like this, IFS equals colon. And now I can iterate through this $path. I can do something like this, and ls will output for everything in that path. It did this field split, and we did an ls of several different directories. And so we just saw the names of all the commands that I can run, by everything in the path. Well, let's pipe that through less so we can see it in detail. All right. So here's all the commands, because ls got, in effect, if we do an echo ls $path, we can see that this is the command that actually got run, and ls saw all the directories and output the name. All right. Any questions about path or IFS? Yes. Yeah. Oh, sure. We can try doing an example, perhaps. So if you set a variable, and say n equals 4, right? You can say echo a is n plus 3, right? Now what happens here is that thing in the $sign gets evaluated as if it were an arithmetic expression and turns into a 7. Now if we do a command, we can say something like I don't know, ls grep I, right? That outputs bin, because that's the only thing that ls has that has a bin in it. And we can say something like this, echo a is $ls grep I, right? And that's going to say a is bin, right? Because all it's done here is it's taken the output of this command and, given it as an argument to echo, and echo obediently outputs it. Now we can parenthesize any command too. So I can say something like this. Whoops. Here we go. Right? And when you parenthesize a shell command, you get basically the effect of the command. It's just parentheses like an arithmetic expression. But if we try to take this rule inside our $sign, right? So what happened to my control key? Let's try it again. So I'm going to get rid of this paren and this paren. Well, I can do it here, right? So here again, I'm doing a trivial parenthesization, right? And we'll get the same output as before because I'm just adding parentheses. But if I add parentheses here, I'm going to be in trouble, right? So by the rule that you can always parenthesize a command, this should mean, the same thing as one of those guys up there. But it doesn't, because the dollar open paren gets treated as the part of an arithmetic expression, and then it looks in here and says, well, that doesn't look like an arithmetic. What's this vertical bar grep? Doesn't look like numbers at all. So you get a syntax error. All right. Other questions about the $sign expansion here? Okay. Yes. because when I changed IFS to be something else, I changed it to be this, right? IFS equals colon. And what this means is we're telling the shell that during the field splitting phase, when it sees a colon in the middle of a word, split it, right? That is, we've done some expansion. $X is expand to something else. You see a colon in here. Well, treat it as if it were kind of like a space separating parts of words, split it into multiple words. So what happened is $path expanded into something separated by colons. Field splitting split each of those things into a separate word, and each separate word got passed as a separate argument to LS. Question? What was the which? Well, all right, let's do the echo first, right? So here we typed echo ls $path. And after variable expansion, this turned into echo ls. And what's my path? UCS something, and then a colon, and then a bin something, and then a colon, and then a user bin. I'm just making this up. You can see the full thing up there, right? Maybe user games, whatever, right? And this is a single word. And if it weren't for field splitting, LS would try to, find a directory with this name, which there aren't in. But as a result of field splitting, this gets turned into echo ls UCS space. You can think of it as a separate word, right? Bin, and then user games and all that sort of thing. So whatever these directories are, now LS will see each individual directory. And when you give LS several file names, it obediently goes and lists out each file name. So it will work kind of the way we want. Question? Yeah, we have to change it back. Well, why is path colon separated? Maybe in hindsight, they should have made it space separated so we didn't have this issue. But it was just set up that way in the 70s, and we don't want to change the syntax now. I guess it is a little convenient in some cases because you don't have to quote it. But if it were up to me, I would make path separate, space separated. It seems like every operating system has a different, like with Microsoft Windows, they use semicolon instead of colon. Why? I don't know. Some person made the sort of the random decision at the time, and we're kind of living with it now. Question? How do I grep what? Oh, yes. Well, that's a good question, right? Echo IFS, right? That is, if you quote it, that's going to get rid of the field splitting. This, this does not occur in quoted strings, right? Double quoted strings, right? None of this expansion occurs in single quoting strings, right? There's no special thing. But in quoted strings, the only things that work are command substitution and arithmetic expression. This other stuff doesn't happen. All right, so to get out of trouble, by the way, what I'd better do now is I better change IFS to be back to what it was, right? So I'm setting IFS back to space tab and new line, which is where we started. Question? Which kind of expansion does occur in double-quoted strings? Oh, well, this one, I'll put little quote marks next to it. These two expansions do occur in double-quoted strings. That's the only one that does. It's the stuff with the dollar signs. I mean, if we go back to the previous lecture, I said inside double-quoted strings, the following characters are special: $, backslash, because you have to be able to escape characters. And obviously the double quote itself is special. There's one other special character, which is grave accent, which is an old syntax for this. You can put a grave accent here and here. I don't recommend that, but it's still a special character. But all the other stuff, all the other expansions we're talking about today do not happen within double quoted strings. They're suppressed there. All right. Well, we've run out of Blackboard over here, but we still have more expansions to do. We have path name expansion. At least that's the technical term for it. I mean, if you go read the standard, they call it path name expansion. I prefer to call it globbing, and I think that's probably a more commonly used term, even though it's relatively informal. But the basic idea here is we will take patterns that look like this and expand them into a sequence of file names that match the pattern. Right? So the special characters here in globbing are star matches any sequence of characters. And it could be the empty sequence, right? A star can match nothing. Question mark matches one character. The bracket expressions of regular expressions also match one character in a set. Except for historical reasons, the syntax here is a little bit different in the sense that if you want to negate a set in the shell, you got to put an exclamation point in front of the set rather than a caret. And that's for historical reasons, right? This is negation. Normally, you don't want to use negation at all. All right. And let's see, one other special thing is there's one special rule for hidden files, okay? And that special rule is that star and the other guys, but this is usually star, does not match a file name starting with dot, right? File names starting with dot are not matched by a pattern that starts with dot. These are the quote unquote hidden file names. The idea is you don't want to be bothered by seeing all these hidden file names. They're there, they're important that they're there, but normally you don't want to see them because they just get in the way. We can see sort of another part of that heritage outside of the expansion issue by looking at the output of ls versus the output of ls minus a. When you give ls the minus a option, it looks in the directory and outputs all the file names in your directory, including those starting with dot. And as you can see, there's, oh my goodness, I have a bunch of junk in here I probably should clean out, like this old .temp file. I don't even know why that stuff is there, right? And for that reason, if you say star.c, it's not going to match a file name .abc.c. The star will refuse to match that leading dot. Yes. How are which files? Oh, well, I mean, this sort of hidden dots thing, it applies to file name expansion and it applies to ls, but ordinarily, dot is just something you can do. For example, I can say, emacs.foo.c, right? And then, int main return 0, right? All that sort of thing. And now I can say gcc.foo.c and run it, right? And get an exit status of 0, right? So ordinarily, dot is just another character in files. It's just that there's this convention in globbing And a convention with commands like ls that they normally don't show you those file names. But other than that, there's nothing special about it. Oh, I see. So let's create a new directory. Make dir XYZ, right? And we'll cd into it, XYZ. And we'll do an ls, there's nothing there. But we'll do an ls minus a, and there's already a couple of dot files in there, right? So these two dot files are super special. I'll talk about them shortly. They're always there. The other dot files that I'm talking about, like .java and all that sort of thing, they are not super special the way that these two are, but they're still hidden. Okay, other questions about the dot files, right? All right. The last part of expansion, and in some sense, it's not even expansion, right? So we went through counting 1.5. I guess this is number 5. The last part of evaluating a command is something else. I suppose I could call it phase 6, but it really should be phase A or something, okay? And this is IO redirection. And the basic idea of IO redirection is that we have sort of some of the words in your command get treated not as arguments to be passed to the executable, but as directives to the shell as to what to do with output, right? And a classic example of that is if you say something like this, cat, foo, bar, baz, right? These two things are just ordinary, arguments that are going to be passed to cat. This thing is something else. Cat won't see this at all. All this does is it tells the shell to send the output of that command to the file baz instead of to the default. The default's going to be to your terminal. And, you can put a space after the graded. Some people like a space, some don't, but it's sort of a style thing. So this is a redirection. And what the shell does before it executes your command is it looks for redirections within that command. And if so, it does those redirections itself before the command actually starts to run. So just as an exercise, suppose we do something like this. Cat foo bar greater than bar. Well, what the shell's going to do is it's going to see this. It's going to create the file called bar and make it empty. If there's a file already there named bar, it'll truncate it to size 0. And then it's going to execute cat with bar being standard output, right? Well, what cat's going to do is it's going to start reading from foo, and then it'll output to bar. And then it'll keep reading from foo and outputting to bar until it's done. And then it'll say, okay, time to read from bar. It will start reading from bar, which is its own output, but it doesn't know that. This part was done by the shell. Cat didn't see it. So assuming foo is sufficiently large, this will go into an infinite loop. Cat's going to constantly be reading from and writing to the same file. Some versions of cat are smart enough to notice the loop and yell at you, but some aren't, and you'll just fill up your file system with whatever junk used to be in foo, repeated over and over again. All right. So you have to be careful, right? This is something that can cause trouble. So the usual IO redirections look like this. This means create or truncate foo. And send output there, right? Standard output goes there. You can probably guess what this means. This won't create foo. This will just read from foo. It will cause standard input to come from foo, right? So this is standard input. And again, when you do something like this, cat doesn't know about foo. It's all arranged by the shell before cat starts running. All cat knows is, oh, you ran me with no argument, and I'll start. That means copy from standard input to standard output. I'll do that. Notice, for example, if you write a command that looks like this, what's going to happen? The shell will arrange for standard input to be from the file foo. If there is no file foo, the shell will yell at you. It won't run the command. But if there is one, it'll do this. Cat will say, you told me to read from bar and output all the stuff in bar. So I'll do that. It'll ignore foo. It doesn't even know foo is there. It thinks, oh, I'm just being told to output a copy of bar to standard output. I'll do that. So this is kind of a dumb command to run because this part of the command is ineffective. Yes.
If the file already exists, it just replaces it, right?
Technically it truncates it. It takes the existing file and discards all the data in the file, right? And then and arranges for standard output to be that file. But for example, if the file is owned by somebody else and you have write permission to it, it'll still be owned by somebody else afterwards because you haven't, created a new file that's empty and all that sort of thing. No, you've just truncated the existing file. Question over here? Why doesn't it output both foo and bar? Because all cat knows is this, right? It knows it's given an argument. And by default, when cat is given an argument, it reads from the file with this name and outputs that to standard output. And it ignores standard input. When you run cat bar, it doesn't care what standard input is. If it was your terminal, it would ignore it. If it's some other file, it ignores it, right? If there are no arguments, it reads from standard input. Or another part of the convention for cat is a minus sign. Stands for standard input. So if we did something like this, cat minus foo less than bar. Oh, well, this time cat will say, oh, you told me to read from standard input and output that and then read from foo. So this would output the concatenation of the contents of bar followed by the contents of foo. And many commands have this convention that a plain minus sign all by itself stands for standard input. Yes. Cat foo minus bar like that. Oh, like this? Yeah, well, in effect, this is, the end of the command. Here's another command. This says, run the command cat foo. It will output a copy of foo into this pipe. Run the command bar. Bar will, when it reads from standard input, it'll be getting a copy of whatever was in foo. So in some sense, a command like this is probably going to be more efficient if you run it this way, right? Because either way, bar sees a copy of the input file. And this way, you don't have to be running the separate program called cat. But otherwise, they roughly do the same thing. Question? Oh, well, let's try it. We'll need something big. So what I'm going to do is I'm going to run ls minus s, which outputs every file and how big it is, right? And then I'm going to pipe the output of that through sort and sort things numerically, right? So the biggest executable in user bin is Emacs. What a coincidence, right? So we can say something like, let's see, let's do this in my home directory, right? So I'm going to touch Eggert/foo, right? And cat Emacs 26.1. and Eggert/foo and send the output to Eggert/foo. Right? And this cat is smart enough to notice that it would go into an infinite loop. So what's happening here is I copied a copy of this file into here, but then I told cat, okay, the next file I want you to read is this one. Please read from this file and copy to this file. So if cat had done what I asked it to, right, here's the output. And the output is going to be this big, long file, right, which is 26 megabytes of data, right? Right? And it's already, oh, I'm sorry. The output is sort of pointing to here. The input is sort of pointing to here, right? So it's already output a whole bunch of stuff to this file. And now I'm telling it, oh, please input from this file as well. So it'll start dutifully copying this data. Eventually, it'll get a file that looks like this. It's 52 million bytes long. And it'll keep reading and it'll keep writing, right? This file will grow forever. Now, GNU-cat is smart enough to recognize that situation. When it saw the second file, it stopped and said, you don't really want to be doing this, right? And I'll bet you if we take a look at the output file, yeah, it caught it about 40 megabytes in and said, no, I'm not going to be doing any more copy. All right, other questions? Yes. I would call this an overlapping move, an overlapping copy. That is, you'll see several sort of restrictions like this in lots of parts of software construction. For example, there's a built-in function in C called memcopy. And the basic idea here is this is the destination. I'll call it D. This is the source S. D points to a piece of memory. S points to another piece of memory. They're both n bytes big. And this says, copy this block of memory over into here. And it does it as efficiently as possible. It's very, if you look at the source code to memcopy, it uses all these weird instructions. But one of the restrictions of memcopy is you're not allowed to do overlapping copies. That is, if S points into part of D, so that it's an overlapping move, then the behavior of memcopy is undefined. The system can do whatever it wants to. You're in trouble. And in some sense, that's what we've done here with this cat example. We've done an overlapping copy, and overlapping copies are trouble, no matter what level of sort of copying you're trying to do. Question? Well, the basic issue here is that in the middle of the copy, your input cursor and your output cursor are pointing to different spots, right? You've got this file. Here's where you're reading from. Here's where you're outputting to. And what cat does is it doesn't like read the whole file into RAM and then output the whole file, because that's inefficient. That requires a whole big chunk of memory, and it just doesn't do it. Instead, it has in RAM just a small block of memory, maybe, I don't know, a megabyte, something like that. It'll read the first megabyte into here, and then it'll copy it over to here. It'll do a write. It'll do a read followed by a write. And then it'll repeat the process. Now the output cursor is here. The input cursor is here. And again, it'll read the second block of memory here, and it'll write that block of memory to here. Now the output cursor is here. The input cursor is here. And it'll repeat. And since it's repeating it all over and over again, it never notices, at least if it doesn't have this checking here, that it's overlapping. And that's why overlapping moves are trouble. Yes? Yes, the kind of stuff we're talking about here is done after all the symbolic link processing is done. Question? Right. Good. That's why I picked a big file. If I picked a really small file, I wouldn't have, wouldn't have had this issue. All right, question.
Like a redirected path, like giving cat the path.
Oh, well, let's try that. So what you're saying is, let's do this and that, right? It figured it out, although here, notice, it didn't know that the input file name was Eggert foo. All it knew is it was reading from standard input. So you got a different error message, but it still found that the files were the same. All right, other questions? Yes. So minus sign is sort of a convention in many commands that says when you see a minus sign as an argument to your command, read from standard input rather than trying to open the file. So if we look at the source code for cat, here's cat.c. Somewhere in here, there's a main function, right? Int main, int argc, char star argv. This is the stuff I talked about in an earlier lecture. This is a list of strings, the arguments given to cat. You might see a loop that looks like this. For int I equals 1, I less than argc, I plus plus, right? Inside this loop, we are looking at one of the arguments given to cat, right? And we can call that, say, the file name, fn equals argvi. Right, so fn here is a string that's going to be, might be a minus sign, which means read standard input, or it might be a file name. Well, you'll see something like this. Let's do a string compare. File star f equals, if we compare the file name to a minus sign, and they're equal, then we'll just read from standard input. Otherwise, we'll go and open that file name and, for readable, something like this. I just made up this code on the spur of the moment. And if you try to compile it, there's probably a syntax error in it or something. But the basic idea here is that the code for cat, the question mark should be down here. The code for cat will treat minus sign specially in the C code itself. It won't treat it as a file name. It'll just treat it as a shorthand for I want to read from standard input. All right, this is a good time to take a break. So let's start up again at 5 past. Yeah, that's the math.
Is this working? All right, awesome. Quick announcement. So the AI Ethics Club will be having a meeting in here tonight at 7. We're doing a prompt engineering workshop where we're also going to be building a website and we're going to populate it with some cool images and stuff. So if you want to learn how to do that, maybe in prep for LA Hacks or something, come out tonight at 7 and there's free tea. Awesome. Thank you.
Thank you. All right, we were doing redirection and I realized that I didn't quite get everything done. So let's do the rest. This is a redirection continued. First off, it's left to right. And each redirection is done independently. So if you say something like this, it's kind of foolish, but you can. This means please redirect from standard input from X. And this says, please redirect standard input from Y. So in effect, this gets ignored, except the shell makes sure that X is there. But other than that, you know, it's kind of pointless. It's kind of silly to do this, but you can if you want. Second, you don't have to have a command. You can have redirection only. This is a valid shell command. This says create 2 empty files, X and Y, and then don't do anything. This actually gets executed, and people do this every now and then. Third, you don't have to redirect, when you're redirecting output, you don't necessarily have to destroy the output file. If you say something like this says, put the output at the end of foo rather than destroying foo's contents, rather than truncating foo, right? So this means append to foo. Okay. Fourth, there is a less commonly used notation for input that looks typically like this. And what this does is the shell takes everything between here and here and in effect creates a temporary file and makes that standard input. So in effect, it's called a here document. And it lets you put, you know, the contents of the file that you want to be as standard input to whatever command you're doing it directly into the shell script. All right. Next one. You can, if you like. Oh, yes, question. You wanted to do what?
Like redirect Y. So I know this command, like the like I know it's not actually doing that, but you're like putting Y to X when you're catting back, right? But that's not what's actually happening.
So here's the file X and it has some X's in it, right? Here's the file Y and it has some number of Y's in it. So what do you want to happen? I'm not quite getting the. This one here? Oh, this this one up here? Oh, well, what this is supposed to do, goodness only knows. I don't, but I can tell you what it does is the shell says, I'm going to open X for input and make that the standard input to cat. This says, oh, I'm going to open Y for input and make that the input for cat, overriding everything else that has already been done for input. So in effect, this thing kind of is pointless, right? I mean, I wouldn't write a command that looks like this.
But okay, let's see, you want to take X and Y, those as input. How would you do that?
Oh, well, ordinarily, I would just write a command that looks like this, but this is a completely different mechanism. Here, all the shell is doing is it's invoking cat with 2 arguments, X and Y. It doesn't even know X and Y are file names. It doesn't try to open them or anything. What cat does is if it sees an argument, it says, oh, you should, I'm going to read this file. So it's up to cat to figure out what to do with X and Y, and then it works kind of the way you want it.
There's no way to like use the arrows.
No, you only have one standard input. So you can't have two files both being in standard input. You have to pick one or the other. Yes. Oh, this one here? Well, for example, you can write this, echo hello world, right? And then, I don't know, TREF, something like that, right? So here you have a string with a new line in it, and echo is given a single argument and just outputs that argument, okay? Which is, it'll output echo new line, world new line, and then we'll run that through TR. Equivalently, you can say this. And then we'll pipe this through TREF. And this is a here document. And the shell will arrange for cat's standard input to be a temporary file, and the contents will be sitting there. And this will output the same thing as that. Question? To this one here? Yeah, this will create two files, right? And or if I say something like, cat, etc., password greater than X greater than Y, this will copy, etc., password to Y, X will be empty after. Question? Instead of doing echo? Oh, well, because if we did a single less than here, then it would try to read from a file named EOF, which is not what we want. We want this TR to be reading data that looks like this. We don't want it to be reading the contents of a file named EOF. So we really need the two less thans here to tell the shell, no, I don't want you to read from a file named this. I want you to read from a file with these contents. EOF is any word you like. I could say Eggert here if I like. All it's looking for down here is a word spelled the same way. And that, in effect, marks the end of the here document. You can put some more stuff here, right? You can say echo foo and all that sort of thing, because this marks the end of the here document. It's just looking for any line that matches the word you have after the less than. Question? Back. In back, yeah. It says direct output to the end of this file. Don't destroy or truncate its contents. This says create a temporary file with these contents and cause standard input to point to that file. And then once the command is done, remove the file. You don't want to bother people with the file. And in front, if I run this command twice, it'll, it's inside a loop, say, and I do it over and over again, it'll create the temporary file each time, a new temporary file, right? Yes. All the shell does with ordinary greater than is it truncates the file. That is, it discards the file's contents. The shell doesn't add any more contents to the file. It just discards it. But it starts up the command, and the command generates some output, and that output will then be put into the file. So that's typically the action there. Question? Yeah, that's one downside of the here document, right? You have to pick a word here that's nowhere in here. And usually you're in control of what's in here, so it's fine, but you just have to be careful. In effect, you can think of this as being like a huge quote mark, right? And this thing is sort of like a huge close quote mark. And you get to spell how the quote mark looks like. Yes. Yes. If you said $X here, it would be expanded. If you don't want that expansion, quote the word. If you quote the word, then all of a sudden dollar signs are ignored. I would just are treated as dollar signs. Other comment? Yes. Well, normally when you see a here document like this, it's going to be in a script, but you can do it at a terminal. It's been years since I've done it. Let me give it a try. All right, so there it created a little here document with 2 lines in it called cat, with standard input being that little file with those 2 lines. Cat obediently output A, B, C, D, E, F to the output. We ran it through TR, which transliterated all the A's to B's. Okay. One other thing is that you can also deal with files other than standard input and standard output. By convention, 0 is standard input, 1 is standard output, 2 is standard error, and there's many more files if you want. For now, let's just stick with single digits, right? So you get 10 different sort of files that you can redirect, and you can say something like this. This says run this command with standard output being bar and standard error being sent to this file, ERR, instead of the default, which is standard error is your terminal. For greater than 1 is the default, and people normally leave it off. For less than 0 is normally the default, right? And people normally leave it off, but you can put zeros in there too if you like. Okay. You can even do trickier things like this. And here, I would like to have TR also affect the error messages. I can do this. This funny notation, the ampersand immediately after the greater than, means change file descriptor 2, change the file 2 to be the same as whatever file 1 is. Right? Since this command is being run as part of a pipeline, when it starts up, standard output is being sent to TR. So this says, make standard error go to the same place that standard output is, which means make standard error go to TR as well. So this will take the error messages from cat in case, if food, it can't be read or whatever. We're going to take those error messages and pipe them into TR as well. All right, and you can cause even more trouble by doing something like this. I do not recommend this, but you can do it. The minus sign here means close the file. Right? This means standard error shouldn't work at all. If you try to write to standard error, that should be an error itself. And this is a very bad thing to do because normally you don't want to discard error messages. They're very important and all that sort of thing. But you can if you want to. All right. One other little combination is you can do this. Here it doesn't make too much difference. It might in other cases. This means please open the file for both input and output. Right? So we can make, file descriptor 1 to be a file that says, well, you can output it, which you normally can, but also if the program decides it wants to read from its output, let it do that as well. It's kind of rare, but you can do this as well. In some sense, what we're saying here is there's a wide variety of ways you can set up the connection between a program and its I/O. And the shell is trying to make as many of those ways sort of available as possible. Question? It says basically make them the same stream, right? And so, for example, suppose cat outputs an error message because foo isn't there. Bar is there, so it outputs the contents of bar. What TR will see is both things. First, it'll see the error message. Second, it'll see the contents of bar, and it'll see that as a single stream. Okay, you've sort of unified the two streams of data here as one. Yes. Here? This line up here? Well, because cat never reads from standard output, because reading from standard output is kind of weird. No, this will act as if this guy weren't here at all. We've given cat the ability to read from its output file, but that doesn't mean it will necessarily do it. Cat just does whatever it's programmed to do. Question? Meaningful ways you can redirect standard input. Excuse me? Why would I want to close standard input? Oh my goodness. Normally you don't want to bother, but suppose you have some sort of suspicious program. You might do something like this, because you're not sure what that program does, but what you don't want the program to do is to access your terminal. So you'd close the terminal this way. To be honest, though, I normally wouldn't. I normally would do this instead. Right, dev null is a special file. It's always empty. Whenever you try to read from it, you get nothing. And, you know, that's probably going to be, I mean, that's a perfectly valid way of telling suspicious, don't mess with my terminal. It'd be a more common way. Yes. Oh, this minus sign here means, you know, take, the default here is standard input because we're doing a read, right? So it's a 0, right? And this means close it instead of redirecting it, from some other place, right? If we did something like this, this says make standard input whatever standard output is. Kind of a weird thing to do, but you can do it. This says, I don't want there to be any standard input at all, which is even more extreme, and it's perhaps a little too extreme. All right, question in front. Oh, well, sure, you can just say foo, right? I mean, that's kind of the more common thing. Here we're opening. Other comment? Yes. Like this, that means close standard output. And again, it's not particularly recommended. All right. So I think we've done enough on the shell. I was supposed to be doing file names and Emacs, so let's at least start by talking about file name. A little bit of terminology issue here. You will sometimes see sort of file names versus file name components. Versus path names. The terminology here isn't entirely standardized, but basically what's going on here is we're worried about file names with slashes in them and what those slashes mean, right? So we have a tree structured file system. And the reason we have this tree structured file system is we got a ton of files. We got thousands, millions of files on CSNET. There's millions of them out there. If they were all just sitting there in one big bag, we'd have to spend a lot of work right? Whenever we did an LS, we'd see a million file names and that sort of thing. So to sort of bring the file names under control, we put them in a tree structure. The internal nodes of the tree are directories. There's a directory sitting at the top called the root directory. Okay, and we can have lots of directories and they can nest as deep as we like. We could have also in our tree structured file systems, files that are not directories. Okay, and they're going to be the leaves of the tree. The most common type of file that is not a directory is called a regular file. So I guess the symbols I'm using here is this is a directory. This is a regular file. But there are other types of files also that can be sitting in this tree structured file system. Two that we'll talk about hopefully today are symbolic links, or symlinks for short. And I'm running out of shapes here. Oh, we'll do something like this, right? This can be a special file. All of these other types are going to be leaves in our directory hierarchy. So they'll be sitting down here, right? We might have, say, I don't know, here's a directory full of symbolic links, but it has a special file in it, and maybe it has a regular file, all that sort of thing. Now, I told you it was a tree structured file system, but I wasn't telling you the entire truth there. Normally it's tree structured, but the leaves of this tree can be shared, right? You can have multiple sort of pointers to the same sort of leaf, right? So we could have a file sitting, say, here, but there could be another name for that file sitting in some other directory. You can even have two different names for the same file in the same directory. All right, so it's not really a tree. It's a tree with shared leaves. It's a kind of an unusual data structure. You probably didn't see this in CS31, but that's what we're seeing here. Okay. And this is the standard form of file system on Linux or Linux-like systems. It's the POSIX standard file system. So far, what we've been doing at the shell level is just kind of treating this for granted. But I wanted to focus a little bit on sort of how this stuff works, because you're going to need to deal with files and deal how the files sort of are created and destroyed and all that sort of thing. When you do an ls-l, which is a very common flag for the ls command, what ls will do is it will take your arguments, or if you don't give it any arguments, it'll take the current directory, and it will tell you all the file names, or at least some of the file names that it finds in that directory. So you can think of each of these directories here as being a simple dictionary or hash table, shall we say. You give it a string, and it tells you, oh, here's the file name corresponding to that string, right? So this hash table might say, right, here's, you know, the string AB, here's the string CDE, here's the string FG. You give this hash table the string FG, and it says, oh, here's the file you're talking about. If you give this hash table the string CDE, it says, oh, here's the file you're talking about, right? It's a very simple model in the sense that you're just mapping strings to files, or names of files to files. All right. Except that the strings that you see here in directories are what we would call, sort of at the file name level, file name components. Right? So if you take a look at an entire file name, or what some people would call a path name, you can look for the slashes in this file name, right? A file name is just a, a byte string. It can contain any bytes you like, except not nulls. Right? A null byte is a byte with all 0 bits. You can't put a null in a file name, but anything else. But you will see occasionally in here some slashes. Right? Maybe you see 2 slashes next to each other. That's possible, right? And then here in between are the file name components. So each file name component is a sequence of bytes that contains no slashes and it contains no null bytes. Right? And it's the file name components that you're going to see sitting here in directories. The way Linux treats a file name is it starts with the first file name component that you have, looks that up at the current directory, and then it says, oh, we better find a subdirectory here. And then it looks this up in that subdirectory. So it walks through your file name left to right, looking up file name components in directories as it goes, right? If the current directory was here, so here's where we start here, right? And if this first file name component is CDE, then what Linux will do mentally is say, oh, we'll go down to here. And if it then sees down here something like QX, it will look for a QX entry here and then say, oh, well, we're now down to here. So it walks through your file name left to right, going down the directory hierarchy as it goes. Now, what can go wrong? First off, it could be that it gets down to here, you say WZ here, whoops, sorry, WZ here, and it gets down to here, and there's no WZ. In that case, it'll say, sorry, this file doesn't exist. It's as if you type the name, QRW here, and there's no QRW at all. It's like the file does not exist. So that's one thing that can go wrong. Can you think of other things that might go wrong? Besides, it doesn't exist. Yes. A file name that's not a what? Oh, so the path, so basically the path keeps going, right? I'm sorry, the full file name has lots more components to go, but you're sitting down here at a leaf, right? Yes. So that would be an issue. So for example, suppose we get down to here, here's WZ. WZ points at a regular file, but we see, oh, there's a WZ and then there's ABC over here. Wait a second. This is a regular file. You want me to treat it as a directory? And it'll say, no, I'm sorry, I can't do that, right? The error message will be something like, not a directory. You specified a file name that lists a bunch of directories in it, but one of the things in here isn't a directory. So that's also an error. Yes. Ah, that's a good point. This has to act like a hash table, right? That is, it has to be a function from a partial function, I should say, from file name components to files. You can't map a single file name component to 2 different files. That's not allowed because that means it wouldn't be a partial function. I say partial function because not every file name will map to a file. Some won't. Yes. Ah, that's a good one. Well, the answer to that one is CD only accepts directory names. It does not accept files. You can't say something like this, right? CD user bin sh, right? Because it'll say, that's not a directory. You can't change directory into it. So since you can't CD into one of these shared areas, you therefore won't have any ambiguity about what directory you're in or anything like that. Yes.
So a leaf directory cannot then be shared by two directories.
Right. The directories are a tree. the leaves, the directory, if you just look at the directories, you'll see a tree. There's no problem there.
And then, I'm sorry, this might have already been asked. It's like, if I take a look at that file.
You'll find it twice or 3 times. Absolutely. Yeah. Yeah. You can find the same file several times. Right? So let's create a situation that looks like that. Where are we now? All right. So here we are. I can do an ls minus l or ls minus al. So what I have here is a very simple file f, right? It only has, well, it has 2,908 bytes, right? So if I do pwd, we can see we are in this tree structure directory. And, here's the root. Well, the U was sitting here. Then there's a CS here. And then there's a FAC here. And then there's an Eggert here. And then down here, there's a CS35L. And then there's a regular file F that looks like that. Suppose I wanted to create this kind of funny situation like this. There's a standard command called ln that will do that. I can say ln space fg, right? So this command, I just run it. The shell doesn't know what it does. It says, okay, I'll run the ln command. When I'm done, what we have is 2 different names for the same file, right? So at this point, oh, wait a second, csfac Eggert CS35L. Oh, we need another directory here, right? So this is F points to here, but we have another name G for the same file. And we can create a 3rd name. I will do something like this, make dir D, ln f d f. And I'll do this. I'll look for in dot and I'll look in D, right? So what do we have here? Dot, which is the current directory, has a subdirectory D and 2 files F and G. And D, the subdirectory, has a single file F, but that F, the other F and G are all actually the same file. Notice they all have the same timestamp. They're all 2,908 bytes. They're not copies. They're all the same file. If I change one of them, so let's make a change. I can say echo something greater than F. Remember, greater than means concatenate to the end of it. And I do an ls minus al again. Notice F got a little larger here, right? It's now 2,918 bytes, and it's got a slightly later timestamp. But that applies to all 3. F, G, and D/F have all been updated because there's just 1 file there. There's not 3 files. There's just 1. Yes. They have unique IDs internally. And in fact, ls will let you see those unique IDs with the -i option. I says, print out the internal identifier for each file. That's this long string of digits. Okay, and now you notice that the F is 242.325.30 because there's just 1 file with that unique ID. So you can use the I is short for inode number or internal number or that sort of thing to find out what those numbers are. Similarly, find will do this, right? You can say find dot ls, right? And it will output everything under the current file system. And you can even tell find to look for a particular file. 242.325.30, right? And it will just output all the names for the file with this particular number. All right, any questions on how that works? So a property of this is that, strictly speaking, in Linux, files don't have names. They only have numbers, right? You can't, given a file, in general, answer the question, what's the name of this file? Because you won't know what it is. It's a file that you're reading on standard input, and it, has 3 different names. What's the name of this file? I don't know. It doesn't really matter. Yes. I use the ln command. When you say ln a b, what this does is it says create a new name b for the file that has this name. And you can run ln 10 different times. You'll get 10 different names for that file. And now it'll have 11 names, that sort of thing. Yes. I did an ln of f to d/f. This created this name for the already existing file f. All right. Other questions on this? Yes. Three and 2. These columns here, right? So one of the columns of ls, it's this column here right in front of my name, is what's called the link count. Okay. And if you think of, a file system as being a graph where the directories are a tree, the link count of a file is the number of pointers to that file. Since our file f has 3 pointers to it, right? d/f, f, and g, its link count is 3. When you type something like this, although it's called remove, in some sense, it's not really destroying the contents of the file directly. All this means is remove a directory entry. What this will do, well, in fact, let's go run it, right? I'm going to run rmf here. Right? And now when I run the find, you'll see that now there are only 2 sort of names for this file in the system. The file's still there. I haven't actually destroyed the contents of the file at all. All I've done here is I've modified the directory, the current directory, so that f no longer names a file. Okay? If I really want to make the contents of the file sort of go away, in quotes, I'm going to have to, in fact, if I do an ls, by the way, you'll see the link count is now 2 for this thing. I'm going to have to do remove d/f. Now the link count's gone to 1, and now I got to remove g. And now finally, that file has gone away. Right? So you can think of the command ln as what it does is it adds, so it modifies a directory to create a new entry in it. Right? That's all ln does, is it edits a directory. And that's all rm does, is it edits a directory. So these commands, although you think of them as sort of creating things and all this thing, they're just modifying directories. That's all they do. Questions on these commands? Yes. Yes, so if we create a new file here, right, like this, its link count is 1. Because when you create a file and give it a name, well, that modifies the directory, right? So there's a directory pointing in that file. And if you look at a typical Linux system, most of the regular files in it will have link counts of 1. Yes. Yes, in effect, the operating system garbage collects the files. Files that aren't being pointed at by anything get automatically reclaimed eventually. Their data are still sitting there on the flash drive or the disk drive. It doesn't bother to actually scrub the drive. So if an attacker gets physical access to your machine, if you remove the file, they can still read the file until you've filled up the disk or the flash drive with something else. But you can't access it in any normal way. Yes.
So, there it says,
Right, because I truncated it as I created it. Yeah. The metadata for a file is stored somewhere else. And that's more of a CS111 issue. But it's not a large amount of data. So for practical purposes, you don't have to worry about it, exhausting the file system. Yes. For the stuff we've seen so far, the answer is no. But there's one new topic for which the answer becomes yes, and you just mentioned it, right? And that's symbolic links, right? So far, what we've been talking about is what are commonly called hard links, okay? They're links that, you have multiple sort of things pointing at a file and all that sort of thing. There's another way to create a link, which is ln-s, the -s option. When you type ln-sab, again, you're just editing a directory. You're modifying the directory. But what this does is this creates a symbolic link, B, that points to A, right? And it'll point to A regardless of whether A exists, right? Doesn't matter whether A exists at all. We're just creating sort of a file whose contents is another file name. All right. So we can see an example of a symbolic link here. All right. So /bin, / is the root directory. There is a symbolic link here. And the contents of that symbolic link is the string userbin. Like that, right? And you can think of this as being a name that you can then use later as part of another file name. So if I say something like this, ls user bin, we'll try it this way. All right. What's going to happen here is we have a file name that looks like this. The algorithm that I talked about earlier has first the special case. If you start with a /, that means start at the root directory rather than the current directory. It sees this file name component, bin. It looks up. bin at the root is a symbolic link. The contents of that symbolic link is usr/bin. Notice there's no slash here, right? What this algorithm will do is it'll take this name and splice in the contents of the symbolic link for the file name component that expanded the symbolic link. They'll say, oh, this is the file name that you meant. Let me interpret that file name instead. So it splices the contents of the symlink into the file name and then reapplies this algorithm to the resulting name. Okay. So it's a symbolic link in the sense that all it's dealing with is file names. It's not looking at components at all, but it's automatically done as part of the file system. Programs, by and large, don't have to know about it. There are a few special programs like LS that can do something special with a symbolic link and say, oh, I'm not going to actually follow the link. I'll look at just the string. But most programs will just treat the symbolic link as if it were the name of the file that it expands to. Now, you can run into trouble with something like this. For example, you can do something like this. We already have this. We can do an ln -sab, ln -sba. What do we have here? A is a symbolic link that says, oh, whenever you see me, I really mean B. B is a symbolic link that says, oh, whenever you see me, I really mean A. That's trouble. And if we do something like this. Oops, cat A. What the operating system did was it did this expansion over and over again, replacing A and B with B, and then B with A, and then A with B, and then B with A. Eventually, after about 20 or 30 times, this is too much. We're in trouble, and it gave up. All right, so symbolic links can be trouble. They can be dangling. They can point to files that aren't there. When you try to open them, and they'll say, I'm not there, and all that sort of thing. You won't have that trouble with hard links. But hard links have their own trouble, and we'll talk about them next time.